Hello, hello. Here is the second video for your final exam review packet. This one is going over Unit 2, Rational Functions. So for these three questions, what we're trying to do is we're trying to simplify our rational expressions completely. So this is multiplication and division. Your first step for all of these questions is to factor everything. So I can look at 23 and my numerator x squared minus 4. That factors to x plus 2, x minus 2. In the denominator, I notice that there is a 2 in common, so I can pull out the 2, and that becomes x squared minus 16, which can factor further. So I'm actually going to cross that off and change it to x plus 4 and x minus 4. And I'm going to factor my other fraction. So since this one has a number in front of my x squared, I'm going to start by multiplying my first and my last term since I can't factor it out as a GCF. That gives me 24. And I am trying to find two numbers that multiply to 24 and add to negative 11. That's going to be negative 8 and negative 3. The method that I use to factor this is going to be the fraction method. So since I started by multiplying by 2, I need to divide both of these by 2. And that x minus 8 over 2, that reduces to x minus 4. And then for my other fraction, since it can't reduce any further, that means that 2 becomes your coefficient for the x. So I'm going to write this as 2x minus 3. And then in the denominator of this fraction, two numbers that multiply to 4 and add to 4 are 2 and 2. So I have x plus 2 and x plus 2. Now, anytime I'm multiplying, what I want to do is I want to cancel out whatever is the same on top that is also the same on the bottom. So I have an x plus 2 over here and an x plus 2 over there that can cancel. I can also cancel the x minus 4 with this x minus 4. And that's pretty much it. So then whatever you're left over with, that is your final answer. So I have this x minus 2. I also have this 2x minus 3 left over on top. On the bottom, I have this 2 with the x plus 4 and the x plus 2. So we ended up with a lot of factors left over, but that's perfectly fine because not everything is going to cancel out nicely. All right, 24, same idea. So in my first numerator, I notice that there is a 3 and an m in common. So I'm going to start by factoring out a 3m. That leaves me with m minus 2. In this denominator, I notice that 216 is divisible by 6. So I'm going to factor out the 6, and that leaves me with m squared minus 36, which once again can be factored further. So I'm going to go ahead and cross this off. That factors to m plus 6 and m minus 6. I'm still multiplying, so I'm going to go ahead and continue to factor my other fraction. Once again, this 7 I cannot take out as a GCF because it doesn't go into 41 or negative 6. So I'm going to go ahead and start by multiplying these two numbers. So 7 times negative 6 is negative 42. And now I'm trying to find two numbers that multiply to negative 42 and add to negative 41. That is going to be, let's see, negative 42 and 1. And then since I started by multiplying by 7, I need to undo that by dividing by 7. So this factor, the 42 over 7, is going to reduce to m minus 6. And then the 1/7 can't reduce any further, so that means that 7 is going to become that coefficient for the m. So this becomes 7m plus 1. And then continuing to factor, this denominator has a 2 in common, so I can take out a 2, and that leaves me with m minus 2. Now let's go ahead and start canceling. Let's see, I can cancel out the m minus 2's. I can cancel out the m minus 6. And let's see what we're left over with. So up top, I have 3m times 7m plus 1. On the bottom, I have this 6 times 2, which I'll go ahead and combine those two. That gives me 12. with an m plus 6. Now you always want to double check to see that it is fully simplified. So if I look, that 3 over 12 can actually be simplified further. 3 over 12 reduces to 1/4. So I'm just going to have m with 7m plus 1 on top and 4 with m plus 6 on the bottom. So always double check to see if you can simplify further. 25 is division, which is very similar to multiplication. So again, we're going to start by factoring everything. So again, this 2 cannot be factored out as a GCF, so I'm going to multiply my first and my last. That gives me -6. Two numbers that multiply to -6 and add to -5. That is -6 and 1. But since I started by multiplying by 2, I want to undo that, so I'm going to divide by 2. And that leaves me with the factors of x minus 3 and 2x plus 1. And then for this denominator, two numbers that multiply to -21 and add to 4 are 7 and -3. I'm still going to keep this as division for now. For my other fractions, let's see, in this numerator, I notice I can actually take out this 3 as a GCF. So let's go ahead and do that and see where that leaves us. So I'm going to pull out the 3. That leaves me with x squared plus 5x minus, what's 42 divided by 3? 14. And then to continue to factor that, two numbers that multiply to -14 and add to 5 are 7 and -2. So I have 3 times x plus 7, x minus 2. And then on the bottom over here, this 2 cannot be factored out as a GCF. So I'm going to multiply my first and last again. So that gives me -4. So two numbers that multiply to -4 and add to -3. Let's see, x minus 4 with x plus 1. And again, since I multiplied by 2, let's undo that. That leaves me with x minus 2 and 2x plus 1. And since we are dividing fractions is the same thing as multiplying by the reciprocal. So I'm going to take this second fraction and I'm going to flip it over. So I'm going to rewrite my first. So I have x minus 3, 2x plus 1 with the x plus 7 and x minus 3. And now I'm going to flip over that second fraction. So the x minus 2 with the 2x plus 1 is now on top. 3 with the x plus 7 and the x minus 2 on the bottom. So let's go ahead and see what cancels out. Let's see, x minus 3's cancel, x minus 2's cancel. And just be careful here because your 2x plus 1's do not cancel because they're on the same level. They're both on the numerator. Same with your x plus 7's. So let's go ahead and condense. Since I have 2x minus 1 or plus 1 twice, I'm just going to write it as squared. Down here I have my 3, and again I have my x plus 7 times another x plus 7. So I'm going to go ahead and condense that and write it as x plus 7 squared. All right, so that is multiplication and division. Let's go ahead and try addition and subtraction. So anytime you are working with addition and subtraction, you need to figure out what your common denominator is going to be. In this particular scenario, my common denominator is going to have the x minus 1, and it's going to have the x from your other fraction. And what you're trying to do is to get your fractions to have the same common denominator. So if I notice my first fraction is missing the x, so I'm going to multiply my first fraction by x. And my second fraction is missing the x minus 1. So I'm always comparing to the common denominator and multiplying by what's missing. I can go ahead and distribute the x. So that gives me x squared plus 3x plus, and I can distribute the 2. So 2x minus 2 all over my common denominator of x times x minus 1. And I still need to simplify my numerator further. So I can combine like terms. So that's x squared plus 5x minus 2 over x times x minus 1. And that numerator cannot be factored further because there are no two numbers that multiply to -2 and add to +5. 27. My common denominator is going to be the 3x minus 4 with the x minus 7. And again, I'm going to multiply each fraction by what is missing from your common denominator in order to create fractions with the same denominator. So this first fraction, I'm going to multiply by x minus 7. And of course, whatever I do to the bottom, I also need to do to the top. And the second fraction, I'm going to multiply by 3x minus 4. Okay, so let's go ahead and multiply out these binomials. So I have x times 2x is 2x squared, x times 1 is 1x, minus 14x minus 7, minus, I'm going to go ahead and put this other one in parentheses since you are subtracting the entire quantity. So x times 3x is 3x squared, x times -4 is -4x, plus 3x minus 4. I'm actually going to keep simplifying my numerator before I write it with my denominator. So let's go ahead and combine like terms. That way I don't have to rewrite the fraction over and over and over again. So I have 2x squared minus 13x minus 7 minus 3x squared minus 1x minus 4. And then I'm going to distribute this negative into my second parentheses and combine further. So I have 2x squared minus 13x minus 7 minus 3x squared plus 1x plus 4. And then combining further, so 2x squared minus 3x squared is -1x squared minus 12x. -7 plus 4 is -3. Now I'm going to go ahead and rewrite my common denominator, x minus 7 with the 3x minus 4. Since my numerator needed to be simplified so much, I just figured I would save that denominator for the very end. That way I didn't have to rewrite the fraction over and over and over again. All right, 28. So 28, I'm going to start by factoring both denominators. So two numbers that multiply to -10 and add to 3 are 5 and -2. Over here, two numbers that multiply to -6 and add to 1 are 3 and -2. I'm going to go ahead and change this to a plus and attach the negative to the 2x. And again, let's look for our common denominator. I'm going to go ahead and write it over here. Let's see, I need an x plus 5. I need the x minus 2. And I need the x plus 3. So my first fraction is missing the x plus 3. So I'm going to multiply the top and the bottom by x plus 3. My second fraction is missing the x plus 5. So I'm going to multiply the top and the bottom by x plus 5. Again, I'm going to go ahead and just work with the numerator for now. That way I don't have to rewrite those three factors so many times. Let's see, minus 2x with x plus 5. And let's distribute. So that's 3x squared plus 9x minus 2x squared minus 10x. Combining further, I get x squared minus x all over my common denominator of x plus 3, x plus 5, and x minus 2. And voila. There's your answer for 28. All right. Next up, complex fractions. So complex fractions are basically just fractions in fractions. So don't let it freak you out. I always like to separate my pieces. So over here, there's my numerator. Here's my denominator. My denominator is already fully simplified, so I'm going to go ahead and leave this denominator alone, and I'm just going to focus on simplifying that numerator for now. I'm going to go ahead and rewrite it. So I have 3 over x plus, and I'm going to write 2 as 2 over 1. Once again, I do need a common denominator, so I can multiply my second fraction by x. That way my common denominator is just x. So in my numerator, I have 3 plus 2x over x. And now that my numerator is simplified, I can go ahead and I can go back to this denominator and use it to simplify my expression further. So complex fraction is just fancy division. So essentially what I'm doing is I'm taking that 3 plus 2x over x, and I am dividing it by that 2x plus 3 with the 2x minus 3. And as we just established, division with fractions, you can multiply by the reciprocal. So I have 3 plus 2x over x times, and I'm going to flip over this fraction, 2x minus 3 over 2x plus 3. And then I'm going to check to see if factors can be canceled. Well, 3 plus 2x is actually the same thing as 2x plus 3, since I can rewrite my 3 plus 2x as 2x plus 3. So these two are going to cancel. That leaves me with 2x minus 3 on top over x on the bottom. And there's your answer for 29. For number 30, again, let's go ahead and circle and separate. So I can see that my numerator is really the only piece that needs to be simplified further because it's separated by two fractions. So I'm going to go ahead and rewrite this as 2 over x plus 1 over 2. And again, I need a common denominator. So my common denominator is going to be this 2 with the x plus 1. So I'm going to multiply my first fraction by 2 and my second fraction by x plus 1. So that leaves me with 4 plus 1x plus 1 over my common denominator of 2 times x plus 1. Let's go ahead and simplify that further. That gives me x plus 5 over 2 times x plus 1. And again, complex fractions, fancy division. So I'm taking that and I am dividing it by x minus 3. Now, x minus 3 is the same thing as x minus 3 over 1. So when I want to multiply by the reciprocal, I now have that fraction that I can go ahead and flip over. So I have x plus 5 over 2 times x plus 1 times 1 over x minus 3. And this one actually doesn't have anything that cancels out, so I'm just going to go ahead and combine it to a single fraction. And there you go. Complex fractions, done. All right, let's go to solving. Solving deals with your common denominator as well. So I'm going to go ahead and list out my common denominator. Let's see, that's going to have an x minus 3 with the x minus 5. And again, I am going to multiply by what is missing. So in my first fraction, I am missing the x minus 5. So I'm going to multiply this by x minus 5. My second fraction, I'm missing the x plus 3. So I'm going to multiply this by x plus 3. And my third fraction, I'm going to multiply by x minus 3. Oh shoot, I wrote that one wrong. Let's change that to x minus 3. Okay. And from here, I can go ahead and just focus on my numerators, since my denominators will all be the same. So I'm going to focus on my numerator. So I'm going to go ahead and rewrite this as x plus 3 with x minus 5 plus x times x minus 3 equals x plus 5 times x minus 3. Okay, now comes the fun part of simplifying this further. So let's see, I have x squared minus 5x plus 3x minus 15 plus x squared minus 3x equals x squared minus 3x plus 5x minus 15. Combining like terms, let's see, x squared plus x squared is 2x squared. Let's see, negative 5x plus 3x is negative 2x, minus 3x is negative 5x, minus 15. equals x squared minus, just kidding, plus 2x minus 15. And I do notice that I have quadratics, which means I should probably get it equal to 0. That way I can factor it. So I'm going to go ahead and move these terms to the other side, but when I do that, I need to subtract, or do the opposite. So I'm going to subtract x squared over here, subtract 2x over here, and then add 15 over here. And let's see what we're left over with. 0 over here. My 15s are going to cancel. That works out nicely. 2x squared minus x squared is x squared minus 7x. And then to factor that further, I have an x in common, so I can take out the x. So that becomes x minus 7 equals 0. So that means my two possible values for x are x equals 0 and x equals positive 7. Now, one thing that you always need to double check with rational equations is to see if you have an extraneous solution. So I'm going to go back to my common denominator. My common denominator is x minus 3 with the x minus 5. And since we can never divide by 0, that means x cannot be 3 or 5. Now, neither of those answers ended up being our solutions, so that means both of these values do work for this equation. If we did end up with 3 or 5 as our x's in the end, then those would be extraneous solutions. So let's see what happens for 32. Maybe this one will have extraneous solutions. Let's go ahead and factor my third denominator. So this factors to x minus 4 and x plus 2. Common denominator is going to include both of those factors, x minus 4 with x plus 2. Let's see, x cannot be 4 or negative 2. So again, if we do end up with those two values, that means your solution is extraneous. So let's go ahead and multiply by what's missing. For my first fraction, I'm missing the x minus 4. Second fraction, I'm missing the x plus 2. Third fraction, I'm not missing anything. So now I'm going to focus on my numerator. So I have x minus 4 plus 2 times x plus 2 equals 12. Let's distribute. So x times x is x squared minus 4x plus 2x plus 4 equals 12. I have x squared minus 2x after combining like terms plus 4 equals 12. Let's go ahead and get it equal to 0. Subtract 12 from both sides. And let's see, get 0 over here, x squared minus 2x, what is that, minus 8. And let's keep factoring. So that factors to x minus 4, x plus 2. So that means my two possible solutions are positive 4 and negative 2, which just so happens to be the two values that don't work. So these are extraneous solutions. So after all of that work, this equation has no solution. So always double check to see if your solutions end up being part of the restricted domain. All right, and we're graphing. Okay, so just like with everything we've done so far, we always want to start by factoring. So I'm going to go ahead and factor both my numerator and the denominator. So this becomes x, let's see, minus 9 with x plus 2. On the bottom, I have x plus 5 with x plus 2. Okay, for the values for the domain, essentially you cannot divide by 0. So that means x cannot be negative 5 or negative 2. Now, your final exam is multiple choice. So your domain might be written like this, or it could be written in interval notation. So interval notation will just take out the values of negative 5 and negative 2. So what that looks like is you would have the interval from negative infinity to negative 5 with parentheses, negative 5 to negative 2, and negative 2 to infinity. All right. Your RD would represent any holes that your graph may have, and holes come from canceled out factors. So I'm going to go ahead and cancel out these x plus 2's. So the canceled out factor is going to give you the x coordinate of the hole. So RD is the hole. If I'm being totally honest, I kind of forgot what RD even stands for. What is it? Something discontinuity, probably. Anyway, it is the hole for your function. So the x coordinate of the hole is going to be -2. And to find my y coordinate, I'm going to take that x coordinate and plug it into my leftover function, which is x minus 9 with x plus 5. So I'm going to take -2 minus 9 over -2 plus 5. And what's that give us? That gives us -11 over 3. So my y coordinate is -11 over 3. Now, for your horizontal asymptote, there are 3 scenarios for your horizontal asymptote, also known as your HASI. It all depends on the degree of the numerator versus the denominator. So if I look at my original function, degrees are your highest exponent, or it's the number of factors that you have. So in this case, my degrees are the same. If your degrees are the same, your horizontal asymptote is going to take the form of y equals a over b. But what the heck is a and b? A and b are your coefficients for your numerator and your denominator. So my numerator has a coefficient of 1, and my denominator has a coefficient of 1. So it's 1 over 1, or just y equals 1. Your vertical asymptote will come from the denominator. So my leftover factor in the denominator is x plus 5. So that means I'm going to have a vertical asymptote at x equals -5. And since I have a horizontal asymptote, that means I am not going to have a slant asymptote or the SLASI. So that's another situation that you could have with your horizontal asymptote. You would have a slant asymptote if your numerator has more factors than your denominator, or if your numerator has a higher degree than your denominator. X-intercepts come from the numerator. So my numerator had a leftover piece of x minus 9, so that means I'm going to have an x-intercept at 9, 0. And then for my y-intercept, I'm going to plug in 0 into my leftovers. So that gives me 0 minus 9 over 0 plus 5, which is -9/5. All right, let's go ahead and start graphing. I'm going to go ahead and graph my asymptotes. So I have an asymptote at x equals -5. 1, 2, 3, 4, 5. And I have a horizontal asymptote at y equals 1. What else can I graph? I can graph my hole. Man, I still cannot remember what RD stands for. That's so annoying. So -2, -11/3. Let's see, what is -11/3 as a decimal to help me graph it? I just grabbed my calculator. So -11 divided by 3 is -3.666666, etc. So I'm going to go to -2, -1, 2, 3. There is your hole. I'm pretty sure the D stands for discontinuity. I cannot remember what the R stands for. Okay, I'm going to let that go. What else? X-intercept at 9, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. And y-intercept at 0, -9/5. -9/5 is -1.8. And with these 3 points, I can go ahead and sketch one portion of my rational graph. It's going to head towards the asymptotes, and rational graphs always have multiple pieces. So since my vertical asymptote, I was going down on the left-hand side. Oh, that's the right-hand side. That means I'm going to be going up on the left-hand side. So there is your other piece. Now, do not forget the fact that your final exam is multiple choice and that you can use a calculator. So you can always plug these functions into your calculator to see which graph or how to create your graph if you really forget what to do. So you would just hit y equals at the top left corner of your calculator, type in your function over here, and that would give you a good idea of what the graph looks like. Now, you might still need to be able to find all of the different pieces. So you might still need to be able to find the holes and the x-intercepts. But if the question was just straight up graphing, like matching a graph, you can go ahead and graph it in your calculator, because why not? Last piece is your end behavior. So for your end behavior, it should always end towards your horizontal asymptotes, because I can see over here, this piece is going to head to 1. This piece is also going to head to 1. So there we go. Your end behavior should always match your horizontal asymptote. All right, let's do another one. And we factor x plus 3, x minus 3. Let's see, x minus 4, x plus 3. I can cancel out my x plus 3's. That is going to give us a restricted domain at 4 and negative 3. So x cannot be 4 or negative 3. Let's go ahead and write that in interval notation. So again, interval notation, I'm just going to pull out that negative 3 and 4. So it has to go in numerical order. So negative infinity to negative 3, negative 3 to 4, and 4 to infinity. RD is for the whole. Your x-coordinate of the whole will come from the canceled out factor. So since I canceled out x plus 3, that's going to give me negative 3. And then I'm going to plug it into my leftover, which is x minus 3 with x minus 4. So I have negative 3 minus 3 over negative 3 minus 4. That gives me negative 6 over negative 7. Or positive 6/7. And once again, for my horizontal asymptote, let's look at our degrees. Our degrees are the same once again, so it's going to be y equals a over b. A and b, once again, are both 1, so y equals 1. Vertical asymptote from the denominator is going to give me x equals 4. And since I had a Hassy, I do not have a Slassy. You can't have both. X-intercept comes from my numerator. What's left over my numerator? X minus 3, so this becomes 3, 0. Y-intercept, plug in 0 into my leftover. So I have 0 minus 3 over 0 minus 4, so that's negative 3 over negative 4, which is a positive 3/4. And we've already established that our end behavior should match our horizontal asymptote. So let's go ahead and jump straight there and put these numbers there, since my Hassy was y equals 1. All right, let's graph. Horizontal asymptote, 1. There we go. Vertical asymptote at 4. 1, 2, 3, 4. And let's plot some points. So negative 3 and 6/7. Negative 3, 1, 2, 3, 6/7 is almost 1. So plot my point right here. That's good. Actually, that was the whole. Let me make that a whole. 1, 2, 3. There we go. Y-intercept is at 0, 3/4. And I have an x-intercept at 3, 0. 1, 2, 3. So I can go ahead and connect those 3 points and see that my curve is going to head towards the asymptote down on this side. So that means it needs to be going up on the other side. All right, and we have one more. Let's factor. Removable discontinuity. I think that's what it's called. I think that's what RD stands for. Removable discontinuity. Maybe. Okay. Let's see. So that's x minus 5, x minus 3. I actually think that makes sense, removable discontinuity. I could totally be wrong, though. I should probably just look it up. Okay, let's see. So my x minus 3s are going to cancel. That leaves me with nothing on top, but really there is something on top. It's a 1 over x minus 5. That's my leftover. So my domain, x cannot be 5 or 3. So I'm going to go from negative infinity to 3, 3 to 5, 5 to infinity. And the whole is going to have an x coordinate of positive 3. Let's plug it into the leftover. That gives me 1 over negative 2, so negative 1/2. My horizontal asymptote. Okay, so this one is actually a different scenario. If I look at my degrees, my degree on top is a 1, degree on the bottom is a 2. Also, on top I have 1 factor, and on the bottom I have 2 factors. So if my degree on top is smaller than the degree on the bottom, that means your horizontal asymptote is going to be the x-axis, or y equals 0. And of course, since we have a HASI, we do not have a SLASI, so that is none. For my vertical asymptote, that's going to be at x equals 5. X-intercept comes from the numerator. This one doesn't have any more factors in the numerator, so we actually don't have any x-intercepts. Y-intercept comes from plugging in 0. So I have 1 over 0 minus 5, which is negative 1/5. And your HASI should match your end behavior. So my HASI is at 0, so that will be at 0. All right, let's graph. Horizontal asymptote, y equals 0. That's just the x-axis. Vertical asymptote at 5. 1, 2, 3, 4, 5. I'm like 99% sure it's called the removable discontinuity. Sorry, I can't let it go. Okay, let's see. Let's plot some points. The whole is at 3 and negative 1/2. 1, 2, 3, negative 1/2. What else do I have? Y-intercept is 0, negative 1/5. And I just have these 2 points. Okay, so I'm going to go ahead and connect these 2 points, but we do know that it should approach the asymptote. So I'm going to keep going down towards that asymptote, and to the left towards that asymptote. And since I went down on the left side of my asymptote, that means on the right side I should be going up. And there's the other side of your graph. And as I said, you can always use your calculator to graph it, just to get yourself, just to figure out what the shape is going to be. Okay, now what we haven't seen so far is the slant asymptote. So for 36, it says, what is the equation of the slant asymptote of this rational function? So let's go ahead and examine the function first and talk about why there's even a slant asymptote to begin with. So if I look at my degree on top is 2, while my degree on the bottom is 1. So in this case, the degree of the numerator is bigger than the degree of the denominator. So that is when you're going to have a slant asymptote. Now, in order to figure out the equation of your slant asymptote, what you need to do is actually divide these 2 polynomials. So I need to actually take x squared plus 3x minus 7 and divide it by x minus 2. Now, there's 2 methods for doing that. You can use long division or synthetic division. Personally, I'm a big fan of synthetic division because it's faster. So I'm going to go ahead and look at that denominator. I want to find the 0 of the denominator, which is going to be at 2, and that is what I'm going to use to set up my synthetic division. It goes in this little half box over here. And then I'm going to list out my coefficients for the numerator. So I had 1x squared plus 3x minus 7. I'm going to leave a little bit space. And then underneath the negative 7, I'm going to put another little box. That's actually our remainder box, because sometimes when you divide, you have a remainder. Now, to go through this synthetic division, your first term goes straight down. So that's 1 I'm going to take this 1 and multiply it by what's in the box. So 1 times 2 is 2. I'm going to go ahead and combine. 3 plus 2 is 5. Repeat the process. 5 times 2 is 10, and my remainder is 3. Now, when you're figuring out the slant asymptote, you actually don't care about the remainder. What I do care about is the 1 and the 5. So now I need to put our x back into it. So I'm going to write this as y equals, the 1 and the 5 represent coefficients for a linear function, since I started with a quadratic. So this is going to be 1x plus 5. And that is the equation of your slant asymptote. So if you were to actually graph this, I'm going to graph it because why not? 1, 2, 3, 4, 5. Your asymptote would be at a diagonal. All right, that's why it's called a slant asymptote, because it slants. All right, a couple more left for this particular unit. 37. So 37, I am giving you the graph and we need to write the equations. Let's go ahead and jot down some important pieces. So I notice right away I have a vertical asymptote, my VASI, at x equals -3. I have my HASI at y equals +3. I have an x-intercept at x equals -2, and I have a hole at x equals +2. And that right there gives me enough information to write the equation. So your vertical asymptotes, I'm going to treat this line as the fraction bar. Your vertical asymptotes come from factors from the denominator. There we go. So that means since I had a vertical asymptote at -3, I have a factor of x plus 3. My horizontal asymptote comes from, since it equals a number, that means it came from y equals a over b. Well, 3 is the same thing as 3 over 1, so that becomes the coefficients for my rational function. X-intercepts come from factors from the numerator. So since I had an x-intercept at -2, that means I have a factor of x plus 2. And holes come from factors that cancel. So that means I will have a factor of x minus 2 on the top and on the bottom. And that right there is your equation for the function. You can always double check that this is the equation, so you can take this, plug it into your calculator, and see if it gives you this graph. It's always a good way to double check, especially since you can use a calculator. That's the best part. All right, last question, I believe, for this unit. Inequalities. So 38, I'm going to go ahead and start by factoring by grouping, and I know I need to factor by grouping because I have 4 terms. So let's see, out of my first 2 terms, I can take out an x squared. That leaves me with x minus 3. Out of my second 2 terms, I can take out a 9, so that leaves me with x minus 3. I can factor further, so that's x squared minus 9 with the x minus 3. X squared minus 9 factors further to x plus 3 and x minus 3 with another x minus 3. All right, and we want to see when this is greater than 0. So what I like to do is I like to make a sign chart. So my sign chart is going to include any of the zeros for your factors. So you have a 0 at -3. I guess I'll just list it. 0 at -3 and +3. So that's what I'm going to put on my number line, -3, +3. And since it needs to be greater than 0 at both of these values, they are going to be open circles since you cannot include them, because if you did include them, your inequality would actually equal 0. And then I'm going to pick some test points. So anything to the left of -3, like -4, I can plug in. Any number between -3 and 3, like 0, I can plug in. And anything bigger than 3, like 4, I can plug in. And when I say plug in, I mean plug into here. So when I take -4, and plug it in for x, what I'm trying to see is if the result is positive or negative. Now, when I plug in -4, the result is negative. When I plug in 0, let me plug in 0, the result is positive. When I plug in 4, the result is also positive. So if I look back at my inequality said it needs to be greater than 0. Well, numbers that are greater than 0 are positive. So I want to pick these two intervals for my solution. So my actual solution will be the interval from -3 to 3 and 3 to infinity. Now, let's say you get to your final exam and you're like, oh crap, I don't remember how to do this. Use your calculator. So what I'm going to do is I'm going to take my calculator and I am going to plug this into my y equals. So x to the third minus 3x squared minus 9x. Oops. Hang on, I'm having calculator issues over here. Minus 9x plus 27. And let's see what the graph looks like. You can't see my calculator, but I can see my calculator. Let me sketch. So I see I have an x-intercept at -3 and one at +3. And my calculator does something like this. It's just going to keep going up, and then it's going to hit 3, boop, and bounce back up. Now, what I'm looking for is, since I want the inequality to be greater than 0, I want the pieces of the graph that are above the x-axis, because these pieces are greater than 0. Now, right here, since it can't equal 0, that means I cannot include this value, which is why your interval has a break in it. So instead of just going from -3 to infinity, I have this piece, that's the -3 to 3, and then I have this piece, that's 3 to infinity. So again, feel free to use your calculators if you forget the entire process of actually how to factor. Similarly with letter B, with the rational functions, again, I can make a sign chart. So I would use any zeros. So I have a 0 from my numerator at 4, and any restrictions from my domain. So x cannot be -3. So those are the two values that I'm going to use for to check my intervals for my sign chart. Now, it can equal 0, so that means I can have the value of 4, but I cannot have the value of -3, because that was from the denominator, and you can never divide by 0. So again, my numerator, this, can equal 0. This cannot equal 0. So let's go ahead and pick some test points. Let's see, I'm going to go with -4 and 0 and 5. And when I plug those in, and again, I'm plugging it into here. When I plug in -4, that gives me a value that is positive. When I plug in 0, I get a value that's negative. And when I plug in 5, I get a value that's positive. And going back at my inequality, I wanted the piece that was less than or equal to 0. So that means I want this interval. So I'm going to go ahead and write out my interval. It goes from -3 to 4, inclusive on the 4, but parentheses around the -3, since that -3 came from the denominator. All right, let's see how we can use the calculator for this one. So I'm going to go to y equals. I'm going to type in my rational function. By the way, if you need to make a fraction in your calculator, hit alpha y equals, and that will give you a fraction bar where you can just input your numerator and your denominator. That's what your calculator is going to show you. So my numerator was x minus 4. My denominator is x plus 3. And we graph. And let's see what this graph looks like. So I can see from my graph that I would have a vertical asymptote at -3. I can also see that I have an x-intercept at 4. And my graph is actually doing something like this. I have this piece and I have this piece. Now, since I want the piece that's less than or equal to 0, I need it to be negative. So the portion of my graph that is negative is going to be the one that is below the x-axis. So that's this piece right here. And that interval goes from -3 to 4. All right, that concludes your video over the Unit 2 portion of your final exam review. Whew, that was a long one. All right, I hope this video helps you out. Stay tuned for Unit 3.